Hello again, physicists. Today's video is titled Of Scales and Elevators. And this particularly is going to address the very common misconception about if you're standing on a scale and you are riding an elevator that is undergoing acceleration, what would the reading on the scale be? Because it would not be the same. Okay, and the reason why ties into this. The fact that the reading you see on the scale is not your weight. That's right. Scale readings, not the same thing as your weight. You have been misled. So let's look at why that is so. If it's not reading the weight, then what the heck is it reading? All right, so for a moment, let's consider the person standing on the scale and then the scale itself to be two separate systems. And we're going to draw out the forces that are being exerted on these two separate systems. Beginning with us. So we know that we have a weight pulling us down, a force due to gravity, Fg. And that we also have a normal force pushing up on us, which would be Fn. And that would be pretty much the end of the story as far as forces acting on us. So we have our weight pulling us down and the normal force of the scale pushing back up on us. Now let's take a peek at the scale and what's going on there. So we have, with the scale, a force F that is pushing down on the scale because of us. So F is you pushing on scale. And guess what? That's the scale reading. The scale is not reading your weight. It's reading how much force you are pressing down on the scale with. We can think of this being the action force. And guess what? If this force F, me pushing down on the scale, is the action force, what would the reaction force be? Well, wouldn't it be the scale pushing up on me, also known as the normal force from our first free body diagram? Yep. So action force, we push down on the scale. Reaction force, the scale pushes back up on us. And what this means is that we can essentially say that the normal force acting on us is the same thing as the scale reading, or our apparent weight. And that normal force will change depending on whether you and the scale are both at rest, moving at a constant velocity, or accelerating up or down. So we're going to look at those possibilities and see how does it change what your apparent weight, what your scale reading would be. Our first example, we'll look at what would your scale reading, what would your apparent weight be compared to your actual weight if you and the scale are not accelerating. So this could be moving at a constant velocity or both being at rest. And usually when you step onto a scale, you are at rest. So if we draw our free body diagram, we would have the gravitational force, our weight pulling down on us, and then we would also have our normal force pushing up on us. And keep in mind that, again, that normal force is the same thing as the scale reading. All right, what would Newton's second law look like here? Well, we would have the sum of the forces, specifically in the y direction. And keep in mind, if I am not accelerating, that would mean my acceleration is 0. So the sum of the forces in the y direction would have to be equal to 0. And if I do the summation, well, based on my free body diagram and my coordinate system, I have a positive normal force minus my gravitational force being equal to 0, or the normal force is equal to the gravitational force. In other words, if you are not accelerating and you step on a scale, the reading on the scale, remember that's the normal force here, will be equal to your weight. And this is why most of the time it's appropriate to step onto a scale, look at the reading, and say, hey, that is your weight. Because in most cases, you're not stepping on a scale in a case where you and the scale are accelerating in some way. Our next scenario, we'll look at what would your apparent weight be if you were standing on a scale and both of you were accelerating upward. So to begin again with our free body diagram, let's not forget our little coordinate system here. If we are accelerating upward, well, we're still going to have a normal force pointing up. Remember, that is the scale pushing up on us. It's also going to be our apparent weight, or the scale reading. And we'll have our weight, gravitational force, pushing down on us. And since we are accelerating upward, this means that the apparent weight is actually going to be larger than our actual weight. That's the only way in which we could have a net force pointing up and therefore be accelerating up. So mathematically, what would that look like? Well, we're going to have the sum of the forces in the y direction equal to mass times our acceleration in the y direction. And we have the same two forces. It will be the normal force minus our weight, and that'll be equal to mass times the acceleration of the system. This term doesn't go away now because we have a non-zero acceleration if we're accelerating upward. Last step would be to rearrange the equations so that I have my apparent weight in terms of everything else. And the truth be told is that your apparent weight, if you were on something accelerating upward, would be your actual weight plus your mass times whatever rate of acceleration you have. Basically, this means you appear to weigh more. So if you are in an elevator and you step on a scale and it is accelerating upward, you will, if you say weigh 700 newtons normally, you would appear to weigh more than that, whether it be 750 newtons or 800 newtons. It's not that your weight has actually changed, it's just that that normal force of the scale pushing up on you has changed. For our final example, we'll now look at what is happening when you're accelerating down instead of up. Free body diagram would still have the gravitational force, our weight, and we would still have a case where we have a normal force. But now if we're accelerating downward, that gravitational force will have to be larger than the normal force of the scale pushing back up on us. We can then use Newton's second law again and plug in our forces. All right, we need to be careful here. If I'm accelerating down, it means that my acceleration in the y direction is technically negative. So I'm going to make this negative. And we know if the acceleration is negative and I multiply by a positive mass, it'll make the whole term negative, like so. All right, and then if I add my weight to both sides, I now see that my apparent weight, if I'm accelerating downward, is actually my real weight minus my mass times the rate at which I'm accelerating downward. And basically this means you'll appear to weigh less than you really do. And in fact, if you were accelerating at a rate, so let's say you were in an elevator, and that elevator, all of a sudden, for some unfortunate reason, the cable snapped, and you were free falling in that elevator. Well, your acceleration would be 9.81 meters per second squared, and your mass times 9.81 meters per second squared would be your weight. So you would be subtracting your weight from your weight. Or in other words, you would appear to be weightless. The reading on the scale would be 0 newtons. And it would be like you yourself also are in free fall. Please review this stuff and be ready to do a ranking task tomorrow. Specifically, it will ask for you to rank the apparent weight of someone standing on a scale in various scenarios where they're accelerating upward or downward or not accelerating at all. Be ready to ask questions as well, since this is a test of conceptual knowledge related to apparent weights and accelerating systems. That's all I have for you today, physicists. So until next time.